In the previous videos, we were finding the areas under curves using rectangles. In this video, we're going to see how to find exact areas under curves by taking limits, and we'll do a few problems to practice this concept. So let's try to find the area under f of x equals x cubed on the closed interval from 1 to 4. Using n rectangles and the right-hand sum, we see that the formula for this is the sum as I goes from 1 to n of b minus a over n times f of a plus I times b minus a over n. This was a formula that you were told to know from the previous video. If we plug in the values on this problem, the function then becomes x cubed, so that means that f of a plus I of times b minus a over n is going to be that value squared, or cubed in this case. And a in this case is 1, and b in this case is 4. So I end up with the sum as I goes from 1 to n of 4 minus 1 over n times 1 plus I times 4 minus 1 over n quantity cubed. This comes out to I equals 1 to n of 3 over n times 1 plus 3i over n quantity cubed. In order to solve this sum, I can pull the 3 over n out of the sum because it doesn't have an I in it. So I'm left with the sum as I goes from 1 to n of 1 plus 3i over n quantity cubed. I can then FOIL out the 1 plus 3i over n, and I'm left with 3 over n times the sum as I goes from 1 to n of 1 plus 9i over n plus 27i squared over n squared plus 27i cubed over n cubed. Remember to FOIL. Now I can split the sum up into 4 different sums. So I have 3 over n times the whole quantity, the sum from 1 to n of 1, plus 9 over n times the sum from 1 to n of I, plus 27 over n squared times the sum from 1 to n of I squared, plus 27 over n cubed times the sum from 1 to n of I cubed. We then just use the formulas for each of these sums, and we can simplify things. And notice that when I then distribute the 3 over n all the way through, I'm left with 3 plus 27 times n plus 1 over 2n plus 81 times n plus 1 times 2n plus 1 over 6n squared plus 81 times n plus 1 squared over 4n squared. If we wanted the exact area, we take the limit as n goes to infinity of this value. Notice that if we did direct substitution, we'd have a lot of infinities over infinities. The first term goes out to 3. The second term, we'll notice that the largest power of n is the same in the top and the bottom, so we're left with 27 over 2. In the third one, the largest power of n will be the same in the top and the bottom, but there's an extra 2 at the beginning, so 2 times 81 is 162 over 6. And in the third one, the largest power of n is the same in the top and the bottom, so we're left with 81 over 4. When I add these all up, I get 255 over 4, and that's the exact area under the curve f of x equals x cubed on the interval from 1 to 4. This process of finding the exact area under the curve is called a Riemann sum. It doesn't matter if you use the right-hand sum or the left-hand sum, as long as you're taking the number of rectangles going to infinity. The right-hand sum, though, is almost always easier, so I suggest, unless you're instructed otherwise, to always use the right-hand sum. We have notation for indicating that we plan to do a Riemann sum. We write this elongated S with an A on the bottom and a B on top, and then to the right f of x dx, to represent the sum of all the rectangles under f of x over the interval from a to b. Notice that this symbol that in the past we've called the integral symbol is an elongated S. The elongated S is supposed to stand for the Riemann sum. We read this as the integral from a to b of f of x dx. So the integral from a to b of f of x dx is given by the limit as n goes to infinity of the sum from 1 to n of b minus a over n times f of a plus I times b minus a over n. Or, using the left-hand sum, the limit as n goes to infinity of the sum from 1 to n of b minus a over n times f of a plus I minus 1 times b minus a over n. The first one is the right-hand sum, the second is the left-hand sum. Let's try another one. So evaluate the integral from negative 3 to 2 of x dx. So this is the same as trying to find the area under the curve from negative 3 to 2 of the function x. If we have n rectangles, then the base is going to be the total length of the interval, which is 5, divided by the number of rectangles, which is n. The right-hand endpoint of the ith interval will then start at negative 3 and will move over the base I times, so negative 3 plus 5 over ni. The height of the ith rectangle is f of negative 3 plus 5 over ni, which in this case the function is just f of x equals x, so we're left with negative 3 plus 5 over ni. The area of the ith rectangle is then the base times the height, and the total area is the sum as I goes from 1 to n of the base times the height. If we simplify this, we can pull the 5 over n out because it doesn't have an I in it, and we can then split up everything else into separate sums. We then use the formulas for our series to come up with the following. So we want to then take the limit as the number of rectangles goes to infinity of our answer from before, which is 5 over n times negative 3n plus 5 over n times n plus 1 over 2. If I distribute the 5 over n through, I get negative 15 plus 25 over n squared times n plus 1 over 2. And we see that, well, negative 15 still goes to negative 15, and in the second part, we have the degree in the top is the same as the degree in the bottom, so the leading coefficients, 25 and 2, are the answer. So we're left with negative 5 over 2. Now you might be noticing that there's something strange about this. We're trying to find what we thought was going to be the area under the curve from negative 3 to 2, but notice that the answer that we came up with was a negative number. We're not supposed to have a negative number. Let's actually look at this problem again. So we just said that the integral from negative 3 to 2 of x dx is negative 5 halves. How can we get a negative answer? If we look at the graph of this function, this is f of x equals x, then we see that the area between the function and the curve from negative 3 to 2 is this red shaded region. And I can find the area of each of these triangles separately. So the right-hand triangle is 1/2 times the base times the height, which is 2. And the left side rectangle is 1/2 base times the height, which is 9 over 2. And notice that our answer of negative 5 halves is the same as 2 minus 9 halves, or the first rectangle of the positive values minus the second rectangle with the negative values. This is because the height of the rectangle for the negative values of x actually give us negative heights. So when we do the base, which is always positive, times a negative height, we end up with a negative area for those rectangle pieces. That means that the integral from a to b of f of x dx only represents an area under the curve if f of x is greater than or equal to 0 on that interval. Otherwise, it represents the sum of all the areas above the x-axis minus all the areas below the x-axis. So for example, if we had this purple curve, the integral from a to b of f of x dx would be the yellow area minus the green area. So we call these definite integrals, and we have several rules for making our lives easier when we're computing them. The first rule is that the integral from a to b of f of x plus g of x dx is the integral from a to b of f of x dx plus the integral from a to b of g of x dx. In other words, if I wanted to add the two functions together, I could just take the area under the first curve and add it to the area under the second curve. The same happens if we wanted to subtract. So if I had f of x minus gx, the same thing would hold true. I would just subtract one integral from the other. The second rule says that if I have a constant times my function, I can pull the constant out of the integral. The third says that if I want to, something's weird here. Oh no, it's not. The third one says that if I want to switch the bounds of my integral, so notice that the first integral goes from b to a. If I want to switch the bounds so that they go from a to b, I have to pull out a negative sign. The fourth one is really the only sort of tricky one. It says that the integral from a to b of f of x dx plus the integral from b to c of f of x dx is equal to the integral from a to c of f of x dx. So notice that if I wanted the integral from a to b to be this red shaded region, and the integral from b to c to be this green shaded region, then adding these two together would actually give me the area of the purple shaded region, or everything. But this also works if b is not in between a and c. So here's the integral from a to b, here's the integral from c to b, and notice that we wanted to go from b to c, so we wanted to subtract off the green area, and we're left with the integral from a to c, which is the purple area. So this actually works whether a, b, and c are listed in order or not.